Hi everyone, how are you? Hope everyone is fine. Um, Sharing the room and so on. So we'll start in around 8 minutes. So thank you for coming. And in the meantime, you can check out our guest speaker's website. He has really amazing research projects, overviews on there that you can check out. They're really interesting. So I really recommend checking those out. Thank you. Hi everyone, we'll start in around 3 minutes. Thank you for coming. In the meantime, I recommend checking out the website that is pinned on top of the room. That is the website of our guest speaker, and you can see there an overview of his different projects he's working on. Hi, Richard. How are you? Thanks for coming.
Hi, Catalina. Can you hear me?
Yes, I can hear you well.
Perfect. That's really nice. Hi, thank you so much. I had a good day. Yeah, so it's evening out in Germany, so it's so everything's nice. I can have a quiet place to participate in the clubhouse.
Nice. I grew up in Germany. I don't know if I told you, but um,
Wow, no, I did not know that.
oh yeah. My parents still live there, and my brothers still live in
Wow.
Germany. So yeah, um, yeah. I'm glad you like it. I'm glad you like
Yes,
living
so far so good.
here. How long are you in Germany now?
Well, it hasn't been long. It's a little bit more than half year, but before, I live in Switzerland, so it's not much difference.
Yeah, that's true. Well,
Mm.
Switzerland is really nice. I like
Mm-hmm.
Switzerland a lot. It's, uh, yeah, I really like it. We used to go every year.
Oh, absolutely.
So you know how to speak German now? Is it?
Not really, unfortunately.
It's not a very intuitive language to learn.
No, before I think I only know how to speak something like can I order like a crispy chicken wrap? Like that's yeah, that's I really have horrible. I did not really pay much attention to that.
Well, it's fine. It's not like it's very useful for the like. It's just Germany, Austria, and Switzerland where you can speak
Hmm.
it. Like,
Yeah,
but
yeah.
you know, and for your work, you don't really need it. So
Yeah, that's true. That's really lost a lot of motivation. Otherwise, I think I'll pay a lot. I will spend, yeah, definitely some time to learn German.
yeah. And is the heat wave over in Germany?
Oh, well, I'm not so sure. At least for this week, definitely. At this week and last week is yeah, last week's it's pretty bad. It's got really hot, and yeah, I have to. Sometimes my my schedule had really changed because it's hard to fall asleep at night. I have to get up a little bit late because then I can have a proper good sleep and then change a little bit working hours a bit because of the heat wave.
Yeah, there's no AC, right? That's the problem. The people
Mm,
don't have ACs in Germany, so
exactly, exactly.
yeah. And then it's very humid. It's like inland, like it's not by the ocean.
Oh,
So
exactly. I think yeah, because I live in Constant, so even worse. I think the lake has a lot of humidity. It's make things quite hot actually.
yeah, but it's such a. It's like probably the best area in Germany to be is Constance.
Yes, this is really a beautiful place, and the lake is so nice, and I even swim in it. It feels really great.
But the lake is kind of cool, though, right? I mean,
Absolutely,
yeah.
Lake
So
Alexa
that's good.
Blast is fantastic.
Yeah. I love Constance, and that region is pretty. It's really.
Well, you must miss the life in Europe now, huh?
Yeah. I do. Uh, and with COVID and stuff, travel was kind of not too much.
Hmm.
Because then you get stuck, and then you're not back in time for work again. It's like. But yeah, I'm hoping to go back to Europe this winter. So, but
Hmm.
mostly to Portugal. Usually, our family then meets in Portugal.
Um, yeah, sure. Around Christmas,
And,
I think that's a great place to visit.
yeah, so usually I don't go much back to Germany, but I have to make time. Okay, I think we can slowly start. And then
Absolutely.
yeah, and then um, maybe next time we talk some more about travel.
Of course, absolutely.
Okay, welcome everyone to Science Society, and of course, a special welcome to you, Richard.
Thank you.
Before we start, let me give our audience a little bit of some information about you so they get to know you a little bit.
Hmm.
And so, Dr. Richard Gu, he's a postdoc in the physics department at the University of Constance, and he works with Professor Clemens Bechinger. Um,
Exactly.
and He studied mechatronic engineering at the Zhejiang University, uh,
Hmm.
and during his bachelor, he joined a Young Scientist Exchange Program in Tokyo Institute of Technology. And as an exchange student, he worked on the microfabrication and electrohydrodynamic systems. And later on, he then did his master's in micro and nano systems at the ETH Zurich. And he did his PhD at Multiscale Robotics Lab at ETH Zurich with Professor Brad Nelson. And during his PhD, he also worked as an editorial assistant to Brad. And his interests in his work or research are magnetic assemblies and structured magnetic materials, swarm microrobotic locomotion, artificial cilia systems, magnetic soft robotics for biomedical applications. And I pinned on top of the room the website where you can find a lot of information about the different projects. But I will switch now to another link, and will post this link then to the chat so people can access it later on. So yeah,
Hmm.
thank you again, Richard, for being here. And
Thank you
usually,
so much, Katarina.
usually before we start, we'll ask a couple of interview questions if that's okay with you.
Of course, of course.
So, when did you realize that like science is basically your life and science engineering? Was it maybe a teacher or some book, or was there something or was it something you always wanted to do and it was always your thing, basically?
Oh, that's a really good question. I did not prepare for that. I don't really know. So I think as far as I see, I was always interested in science, and I have a pretty strong curiosity. So sometime I always want to know, try to dig the bottom of it and see what's the mechanism working behind the world with with this with the machines for everything I encounter. So I always have this very strong curiosity. And then when the years pass, I'm getting more and more interested in the. Oh, can you hear me?
Yes. Mm-hmm.
Oh,
Yeah.
oh, I see.
Okay.
Sometimes I lost your feedback. Okay, excellent. So over the years, I get try with different ideas, and I have in the certain stages, I was getting more interested in realizing my ideas. And I think scientific, especially in engineering communities, are really there are many interesting things going on in the robotics, and you can just I think to me that there's nothing more fun than just make some of your own small setup and machines and watch it move, right? You build your own robot and watch it move. I think this is really fun and exciting to me. So yeah, I think that's how I interest in science and engineering in general.
That's interesting. um And yeah, I agree. It is wonderful. I used to play with Lego a lot, and
Me
yeah,
too. Yeah.
and um, and And then from that, how is there maybe a story behind these projects? How did you come to work in this specific field then, or work on this specific project? Was it kind of easy to get grants for it? Is there maybe a background story behind this project?
Oh, yeah, that could be, that definitely, I think the reason lead me to this lab, or, the way I did my PhD in Zurich is, I was reading the news or the papers at the time, and I really find something really exciting that people make this microscopic machine and how can move it. And it and I get used to this like a microsystem, which you use the microfabrication techniques to make something fabricated in small scale, like a well, of course, initially they are originated from this integrated circuits to more like photolithography, microfabrication, and then many mechanical engineers join in the community to try to make something, a mechanical system that is functional, like this digital mirror arrays for the projectors. Just many successes also for with this like MEMS gyroscope sensor that which is in iPhone right now. And the field is really gradually evolving. And around 10 years ago, this microrobotics really coming to, I think that the stage is uh, people, I mean, they know how to make, let's say, static structures. You can integrate many micro or actuator into a system which is overall on the chip, which is not really moving. But then consider another case, like how to make something like mobile and move along the way. And that really like this idea, which some people say they can be traced back to this fantastic voyage with this all the this fiction movie, but I think they're really just the curiosity how you can make something move, make a really small scale object move in that scale that you have very limited space, that you cannot put standard method. You can have a battery, have an actuator, have a sensor, have a microcontroller to put into a small, very, very tiny microscopic object. And then they trigger a lot of fundamental question how to make the move. And then engineers, especially like what at that time, I think my supervisor Ben Nelson was really a pioneer in the field. They propose many ways, especially use magnetic methods to control and move the small scale objects. And that was really exciting for me because you just see how they get inspired by nature and create this all this stuff. So I think this kind of the idea, uh, that to engineer in the microscopic system that we don't encounter in everyday life, right? So what we encounter is more like a meter scale or at least a centimeter scale object. So our intuition, which we gain from the daily life, they are not very useful in terms of design small scale objects. And sometimes it could be super counterintuitive because the scaling effect, right? At the small scale, like the viscous is really dominant and the things can change drastically. And that's how let's say, of course, for as an engineer, if you don't find a good solution, then you look at nature because they already optimized after millions of years. And then people start to mimicking the bacteria, flagella, how to make things move, or the sperm, how they propel. And this whole field just started. And then people right now, people are in the stage to explore potential application for that, to use those kind of micro robot to make potential medical application to carry drugs, to as lab on the chip manipulation, micro manipulation. It's just it's a whole quite a large field actually.
Yeah, thank you for giving us that wonderful introduction. And it's so fascinating, such a fascinating field. So I can't wait to hear your presentation. So the link for your presentation is now on top of the room, so everyone can access it. And yeah, and the stage is yours. Um, and thank you.
Thank you so much, Katarina. And this is like ask this very general question to guide the audience gradually get familiar with the work that I will introduce today. So I think as I explained, this microrobotic is getting quite more and more interesting because their potential to be used in the human body. And also, as a roboticist, we use this magnetic field. We control them through external magnetic field. So our lab not only make the small scale micro robot, but we also focusing on this magnetic system, which you build electromagnetic coils and you generate. You pump into the different current, and then you can generate different magnetic field around these electromagnets, and then by properly control them, you can have the desired magnetic field as you want. So those systems, they're all very crucial to the applications, and we are there. I think the whole field is also, we are gradually moving from the stage that it's already very exciting to make small scale move as you wanted to thinking about the potential impact, how we can translate this to, let's say, any kind of medical application, because this kind of precision drug delivery, like this swallowable micro doctor that can just navigate inside the body and find the tumor or find whatever they want and to do the treatment, is a very a very exciting dream to drive many scientists and engineers to working towards that direction. So today, I would like to introduce our recent work on this direction, some recent development on in this background about how we can robustly control those microrobots or deliver those microrobots into inside the body in a very unpredicted environment. So I will start with this: A Fantastic Voyage. It's a very old Hollywood movie, which actually probably very early they think maybe not the first, but definitely the pioneers think of how to shrink small scale machines down and send humans into doctors into the human body and do the treatment. And this movie, many people really like it. It's actually pretty good, very successful at the time, and they really planned this idea into the society that maybe one day someone can realize that, and it is because a lot of work has been realized they can use bacteria inspired this helical propulsion, like just like a corkscrew motion, same principle as the bacteria swim, or make something like a rolling mechanism, like some small roller they can self-assemble and then rolling on the surface, like how the wheels move on the ground. So those are so many type of, but this need a surface. Those type of locomotion mechanism has been developed to drive the small scale machines to move, and we already see those some of maybe more small scale lab on the chip applications. But if you really think to put yourself on board with these micro machines in the human body, I think this voyage is not so fantastic because it will be a chaotic case. Those machines, at least for what we developed so far, they have a relatively slow speed. They basically typically a couple of body lengths per second, and they are really in a very small scale, like micrometers. And for example, in the blood, as the image proposed, that they have a flow, and this flow is not constant speed. We have a pulsatized flow, and they also, because have a blood vessel, so close to the vessel wall, the flow speed is zero, and in the center is the highest. So there's a shear flow there, so they can reorient your body. So if you're on this fantastic motion mini machine, a micro robot, a micro machine, micro vehicles, you're probably gonna have a very hard time. If you are as the same as a car seat like I have, then you will have a hard time. And also, those small scale micro robots, they are foreign object. They are not interesting in our body, so they're going to trigger some kind of immune response. So let's say macrophages can just capture it and eat it. Basically, they will not let them just pass by. And also, you have blood cells, you have different types of fibers. They can get jammed, they get stuck. Many things can happen to the small vehicle. So if you think of this, this is really challenging and on the board when you be in high risk. And also, what's the worst case is they'll just get lost, like they lose connection to the external controller, and then you cannot find it anymore because they're just tiny, like let's say similar with the cell scale. So it's also likely we're not able to find it anymore. And those challenges even get worse if you consider you want to deliver a lot of them into the human body. So for the swarm control, you have many of these vehicles, and then those individual control, but you only have, let's say, for magnetic microrobot, you only have one global magnetic field to control everyone. And they usually, those machines have intrinsic differences due to the fabrication differences. So they will very difficult to control many of them, although there are some very promising progress in the direction, especially in the Chinese University of Hong Kong and the Lijiang's group. There are many very promising direction for swarm control. But overall, this is still a very, very challenging job. And I'll be really surprised to see someone can robustly deliver this to the body. And also, if you think of more realistic scenario, if you have some risk that potential get lost your foreign object, it's very hard to get approval from the regulatories either. So because that will be so those many challenges limiting their future to implement such a fantastic voyage into the real human body. So I'm going to move to the next slide. So, so if you think of really like we are at the stage to think of how to implement further into the human body, and I would just use a recent publication that for magnetic guide wire for example, stroke treatment, they're usually composed of a couple parts. First, you need to have a magnetic actuation system which provide this global magnetic field which drives this our whatever magnetic microrobot inside the body. In this case, they are magnetic guide wire, but in the previous case, they can be a helical shape, this microrobots. And this is the first part. The second part is the microrobot itself. Of course, we need to inject it somehow or like this through the vein that we can gradually push through the blood vessel in this interventional surgery in this case to navigate inside the human body to reach the target position. And the third part, which is also very important and people rarely talk about, is this fluorescent fluoroscope, because we need to track where they are. You need to image, especially in this system structure, that this fluoroscope need to be is probably the only available and robust feedback. I think ultrasound is also many people look at, but the image quality, the resolution, they also play a role there. So in that case, I think still at the current stage, the fluoroscope is the most promising one. And that also means we need to get exposed to the X-ray, maybe a little bit, the dose will be fine for the patient, but for the doctor, that could also be a one concern. And then you will have an image for where the microrobot are, right? And then you combine as a feedback mechanism. This imaging will provide, let's say, the real-time position. So this feedback from the fluoroscope image is not only the position, also the time is also important. If you can imagine when they're in the arteries, which is like flowing very, very fast speed, then you need to have a very fast tracking as well. Otherwise, you can potentially lose it. So all this, you can see there all these parts need to work together to have a potential application of this microrobot into the human body. So I just use a very inappropriate analogy to this process, like use a drone to deliver a package in the storm day, which you have the wind, you have the thunder, you have the rain, and then it's just really, really, really difficult. And especially this in vivo environment, you have all this blood cells, you have all this immune system response. So you are not doing an easy job in a very or lab or in a very well controlled, well known experiment. This is really challenging because there's so many things is out of our control, and it's a very nasty environment. Also with very limited access, we only, let's say right now, the robust feedback is the fluoroscope. So, so all this poses so many different challenges. So I just make it sound really, really difficult. But if and also, so all those three aspects, if you understand actuation system, those aspect is when you think of designing the actual micro robots, all these three aspects need to be considered. For example, as I explained, you need to be driven magnetically. That means you need to have magnetic material on the micro robot, right? So I already go to the slide number 4. So those magnetic material provide a driving force and torque for the micro robot to move inside the body. And if you want it to overcome a very strong flow, of course, you need to put more magnetic material on it so it can be driven more strongly through the external magnetic field. And the other part is the cargo material. For example, typically there will be a drug, or in certain cases, it can be magnetic nanoparticle for hypothermia. But whatever we want to do, there also could be the other materials that we want to carry on. That's actually the target material. So we want to put enough material for this. If there's not enough material on one single robot, then we need to implement many of them, right? So that's also put challenges. And for many cases, I think for many applications, the drug need to have a minimum concentration locally, even though you're doing a local delivery, but you still need room to put this cargo or the drugs to on board with the microrobot. And the last part, as I said, the third part is about the use X-ray tracking. And usually we put this X-ray contrast agent onto the microrobot so we can see it more easily through the X-ray. So also, if you want higher temporal resolution, you also need to put more, because then the amount of the X-ray you apply is also sufficient to see where they are in the real time. So all these three material is necessary to put a very, very limited space, which is typically a cup as roughly as the same scale of the cells, let's say a cup of hundreds of micrometer or tens of micrometer. They're thinner or smaller than a hair. So those small material need to put all of three, and they are, they are kind of, we need to make optimization and have to compromise between those three. So that's why so many of the research paper or many of the public, even very high profile publications, they don't tell you this big picture. And what they do is when they talk about this biodegradability or how much cargo they can take, they use this polymer, let's say the polymer to fill with the whole this helical structure, and they coat it with a little bit of magnetic material, so you can carry tons of drug on that, but you will be extremely weak in the magnetic field. So that's how they demonstrate their degradability, including us the same. And also, when you talk about those microrobots can overcome the blood flow, what they do, they use a pure of almost pure nickel sphere, and they coat a thin layer on the outside. So of course you're very strong because you're all the volume is used for magnetic material. So they're very powerful to drive in the external magnetic field, but then the drug you actually coated on the surface is very limited. For certain applications, fine, but there are many other applications very limited. And of course, you can imagine that, let's say, nickel is not really biodegradable. So if you think of in the body, that is really not, you can imagine to use that. So usually people make those compromises. And when they want to show the strength in one direction, they just do it really well, but they don't really talk about the other direction. And so I want to propose something different. We can try to break out this framework to do something a little bit different. And for the robust, so then you can think of this is if you have mobile delivery, it's so difficult. Can we think of something more robust? Of course. So as most of medical application, you want to deliver liquid or extract liquid, you use medical catheter, and those catheter have so many methods to drive. Some of them have internal the pull wire, so you can tilt it like in the standard endoscope, or some of them can be magnetically guided. So there are also some works from our group is working on that. So you can use external magnetic field to guide, similar as I showed you previously, to show this magnetic possible guide wire. And if you have this lumen as a medical catheter, as you can imagine, you can just pump whatever drug or anything through the inner lumen, right? So that's really like the most robust method ever. Like blood, let's say, they will not have a direct, because they're just sealed, they're encapsulated. There's nothing can direct interact with this in vivo environment. So, and this is also compatible with a magnetic navigation system. So they're pretty ideal, but this also have a disadvantage, especially consider something small, is there's a law called Hagen-Poisson flow. So if you shrinking down the dimension to it at the micrometer level, the drag is so high that the pressure is incredibly is prohibitively high, that they will not allow you to pump in a very fast speed. So everything will be kind of like it's like pumping like a glue or honey through a very small, you use a straw to drink honey from it. That would just take like forever. So that is the limitation fundamentally, and you can see from the equation. So the pressure drop is inverse proportional to the radius of the tube of 4. So this goes pressure. The pressure required to pump the sufficient amount of drug increase very rapidly when you shrink it down. So at small scale, that is not something really ideal. So consider all of this delivering challenges. We're looking at nature for some potential solution, and one of the well-known example is this intracellular transport using the microtubule and the kinesis motor, also with the dynamotor. Lets it walk the opposite directions. I think there are a lot of biologists in the audience, so I would just try. I will not explain too much on that. So and then there's some famous video that for visualizing this process, I think is really fantastic. This kinesis motor has this two domain, and they can alternately bond with a microtubule to walk forward. And this is really beautiful to see. And of course, this process costs energy with ATP, but this is highly conserved and they are applied for almost many cells. In certain cases, for example, the neural cells, we have really, really long, and they can also deliver this cargo to the end of synapses, if I'm doing call it correctly, and then they can release this chemical signal to trigger the next neural motion. And this can be like almost as long as half meter. So this must be a really robust transport mechanism along that, and we want to mimic it. And another way, if you think conceptually different than the medical catheter, is the medical catheter using tube structure to isolate it, whatever inside the tube and outside the tube. But in the cell, because they're so small, of course, microtubule is a tubule, but what they do is they are not transport anything inside the tube, but they transport it outside. So it's more like I'm climbing a rail or a track, and then I'm dragging another thing with me. So I think this idea, something from inside to outside, is also very inspiring, because then I'm thinking, can we just do something transport from outside instead of the inside? And then this lead to us to make this magnetically artificial microtubule that we make this a fiber using a very standard materials called SU8, is just for micromechanical systems. Very easy to process, well-established method. And then we electroplated, there are some magnetic posts inside this fiber. So this fiber has a lot of holes, but then after electroplated, then they are inside. And then if you put anything, let's say outside as magnetic material close to this artificial microtubule or this synthetic fiber, then this magnetic under a certain magnetic field, then your object will start to interact with this your artificial microtubule fiber. And this magnetic interaction, usually they can be attraction. So in this case, we make them all soft magnetic material, which means their magnetization is completely determined by the external magnetic field. And as you can see, in the figure, basically the rod, which we will just rolling under the external magnetic field, will using this small tiny magnets inside the fiber as an anchoring point to propel forward. So a little bit like a stepping stone. So when the magnetic rod micro rod is on this post, on this magnetic post inside the fiber, they are really like stuck because they're really strong magnetic interaction between them, and they can use it to propel forward. So most interestingly, because their magnetization is dynamic, so it's not like when I'm walking on the gluey surface that my feet will be glued completely on the ground. Those magnetic is dynamic, so they can be turned off as well. So when there's like oscillating on and off, on and off. So when they are kind of off, which means the magnetic field is perpendicular to this nickel plate, the magnetic direction is really small. So those rods can propel step by step forward. So they also give them the chance to release it, very similar to the kinesis motor mechanism. So this kind of stepwise attraction and the release, this kind of motion design, they're really like give us some quite surprising result for us. For example, they are walking so well, so we have to use this almost 99% or almost pure glycerol to test their dynamics, because we want to capture what happens if you cannot overcome the drag. Because in the water, they just always keep on track with this motion. And they're really like, so they rotate one cycle for every 2 steps. So basically, every time they go half rotation cycles. They will go one step at very low speed. And then if you go to slide 7 and play the video, you will see they really like, Olympic swimming, then all these micro robots start to move to the right, and you see at the different frequency conditions. So for very low speed, of course, this rod will just like a flip, step by step, follow a perfect, this half circle trajectory, and they move forward. But of course, as all the micro robot, if you increase the rotating magnetic field speed, they will keep it up at a certain level. They will start to lose track. They will not able to keep the field, keep your step anymore, because the hydrodynamic interaction get really dominant. They will just slow things down. And in this case, we provide a very good method to explain roughly, especially from a fundamental point of view, a modeling to explain what is going on there. So there are actually two types of asynchronization here. One is this lead translational asynchronization, and the other is a rotational synchronization. We also provide a model to explain how to predict those transition synchronization. And the result is those microtubule, if you have this micro rod on the microtubule, this is a spinning motion, they really provide a fast and a robust locomotion. So by saying fast, we need some comparison or some benchmark. So we develop this value, which like a normalized value, we call it z value. So it's a velocity divided by the frequency and the length. Basically, it tells you how many steps, how many translational motion they go by giving you one certain rotation, how many body length they walk forward, basically. And this really put the result on top of with many other comparisons. For example, many of the micro swimmer, they slip, which is not really a surprise because, for example, it's how can I say, for like surface roller, because there's a liquid layer between the micro robot and the surface. They will not like glue on the surface to move forward. They're more like as a person, I'm running on the ice. So each step I make will not be a full step. Instead, they will just be make me fall a little bit. So if I run really, really fast, like this cartoon movie, um, um, that I may be able to go very fast, but this is highly inefficient. But if you bring this micro robot, this micro roller, especially this rod structure, onto the artificial microtubule, you will significantly increase the speed. So in our case, we roughly about an order of magnitude, about 10 times higher to the other magnetic micro swimmer as a comparison. And we think this is a really interesting and very shocking result because in this way, if you think of this triangle structure, as we said before, if you want to make a micro robot, you need to make a lot more magnetic material, but you make other sacrifices. But now, if you put this on the microtubule, artificial microtubule, you don't have to make those compromises. You just bring your speed to the next level using this. And what is more interestingly is those microtubule provide a guide because they're constantly attraction force between the micro robot and the artificial microtubule. So they will always get somehow close by. They will not just easily to lose track, even though what we show they lose track, but they are talk about horizontal motion. They will not easily to be just fly by washed away by the blood. So this kind of, and we also tested experiments which we just use a static field, and those micro robot really just get anchored on one of the plate, which very, very hard to move it. We have to apply insanely high speed of the pure glycerol to wash them away. And as I've mentioned previously, the ideal case will to be used in a blood. So and the blood is to have the flow. So we need to test them under a more realistic flow condition. So this flow is not just a hydrodynamic drag force, but it also apply a shear force, which they're trying to bend this micro rod as well. So as I put in the slide number 9, the micro robot really just rolling on that, even under the very external strong flow. And we measure this flow, locomotion speed and the external flow speed under the different rotating frequency and see how it behaves. And we provide the theoretical, if you're interested, you can read the supplemental material. We have the theoretical prediction showing how this external flow influence this locomotion speed. And we also observe something interesting, they have this like 2 stages. There's some details quite interesting for like sleep and the it's really fun to see how they cope with this drag, and you really feel sometimes this microbots like struggling to hold on to this track, and but unfortunately they're not strong enough. They have to be washed away. Uh, but all these experiments, we are trying to explore the boundary for this because there's so many interesting dynamic happening which we did not understand before. So we are really using some extreme condition which is not will be the same in the real body. For example, the glycerol, 99% glycerol is about 1,000 times more viscous than the water. So because we want to capture this full dynamics, that's why we use these really extreme cases to understand this physical system. And then you can and if you and the result for this end of the flow condition is really striking because they're very similar to the natural microtubule flow dynamics. So if you see the slide 10, there's some really pioneering work around 2000 that is really the single they use optic tweezer to measure the force that you can apply to the single kinesiomotor walking on the single microtubule. So when the kinesiomotor walk, then they use the optic tweezer to apply this optic force to hold this bead and see how fast this bead move along with it. So they have this famous load versus velocity plot, and they measure like what is the low the force to hold back so the kinesis don't move anymore further. And I think and this decay like with a higher load, the lower velocity, this almost, let's say, the linear this decay is very similar for what we observe under the flow. So in that case, they use optic tweezer to apply this load. In our case, we use external flow to apply the load. So we also have we are now, let's say, it's not like some machine. If you just apply some load over a certain range, they will just crash, right? But in this case, they're kind of gradually slow down into zero speed, and then they will just keep but you already have a much improved compared with the local flow speed. And also in certain cases, for example, this for 0.2 hertz, very slow speed, you also see a little bit like a plateau. There's a weak dependence on the load force at this lower external load conditions. And I find this really amazing and striking because this artificial microtubule is used completely different mechanism. We implement this magnetic interaction, and we are in a very different scale. We are about a micrometer, or so the typical periodicity. If you're interested, they're really just like a 90 micrometer in the periodicity, and the width and the height of the microtubule is about 80 micrometer times 50 micrometer. So they are slightly thinner than a hair. Well, if your hair is really thin, then maybe it's similar. So they're really like a hair dimension. But in the natural microtubule, they're like the diameter is about 200 nanometer. They're really like 20 nanometer. Sorry, they're really like small scale, nanometer scale. But when you measure the dynamics, they're just strikingly similar. So I find the similarities very interesting. Um, and following this, we also study this kind of swarm local motion behavior because when we use small micro rod, this micro rod is the same length as the periodicity, so they're all at the micrometer scale. So we are thinking, can we use this to transport smaller cargo? So we use this magnetic microspheres, which is really like a polymetric matrix. And they have a bit of iron oxide nanoparticles, which is already get approved by the FDA as this is biocompatible materials. And then they are very weak in terms of magnetic interactions. And then we just spread it out and then apply a field. If you play the video, you will see they will start to assemble at around the microtubule, because around this microtubule have a very strong magnetic field gradient. So all the particles will be drive too close to those places, and when they accumulate large enough, they will start to move between one plate to the other. So this is really like a self-assemble a process and a collective transport behavior allow those swarm of microrobots to move from one place to the other. So you can imagine if you have a really tiny particle, they will not move, because when they move halfway, they will just pull back under the next cycle. But if you assemble something large enough, so there's a critical local density, or you need to assemble to a certain size to allow you to transport from one plate to the other. And we also have roughly quantify what is going on there, even though this is a really hard, complex process to understand. And this is also, we observe this behavior in nature, because in the cells, when sometimes the cells transport a very large cargo, they don't use one kinesin protein motor, they use a couple of them. So it's like a lot of kinesin motor drag the same large cargo at the same time. So, and they find there's a collective behavior. If everyone drag at the same direction, then it's better force, because you have less fluidic drag to overcome. You have this hydrodynamic coupling behavior that allows everyone to walk at the same time. So this behavior is very similar to this, like a bike rider in Olympics. So the other bike rider can hide from each other, so you can reduce the wind drag, because they ride at a very high speed. In this case, the drag is also very important. So when you hold a line and walk next to each other, then you have a much higher chance to move to the next step. So this is also interesting behavior that we did not expect before the experiment, and we find it out. It's just a very interesting result. And very end, we just, to help people understand what this could potentially use, we make a very artificial system. This is not very realistic. We did not reuse the real blood, so we make some microfluidic channel using PDMS or use an SU8 for PDMS microfluidic channel, very standard things. And we try to show this can be inserted into a small channel, and we turn on the global field, and you can see there's a swarm of these particles follow the guide with the artificial microtubule and gradually accumulated at the end. So we think this kind of showing an idea in the target delivery. So basically, the process is you first, of course, you use a microcatheter, and then when you go to the area which your microcatheter is a little bit too big, they cannot fit into the smaller vessel, then you push through this kind of as a guide needle, or like a small microfiber, and then you push through with the help of magnetic field into the target vessel that you want to deliver your drug in, and then you turn on the magnetic field. Every drug will just follow the track on this artificial microtubule and don't go to the targeted location without losing in the middle. And this idea can really provide this precision delivery to the next step, because using this method, you can be more precise. If I don't know what exactly the realistic case the need for this, but let's say if you have a really small tumor, you want to kill it at a very early stage, and the artery which feeds this small tumor is super tiny, then this could help your way to guide the drug that into the targeted position, and only harm the tuber, not the other branches of the blood vessel for the nice vessel cells. And we think this technology really fit into, like what I show here in the slide number 13, the gap between the traditional medical catheter and the microrobots, because microrobot can move, but they cannot overcome some very strong flow, especially in the small artery. And for the medical catheter, they are very robust and very well developed, but they cannot be easily shrinking down to the micrometer scale. So we think this artificial microtubule can really bridge the gap that to continue the full coverage, let's say in the future potential applications. And in that case, you can imagine everyone will like nicely walk on the artificial microtubule without get lost. So in another way, you can imagine using the fluoroscope, you don't have to like worry that things kind of lose track, they will be washed away all the time. You don't really require the feedback signal from individual microrobot, the position, but you can just rely on it will roughly walk on the microtubule, and then I just use the image as feedback to showing, oh yeah, things walk nicely without worrying too much. It's not like you heavily depend on the feedback signal for control, but in this case, they will just walk as it is. So I guess I already spent quite some time explaining this. Yeah, so if you're more interested, I think maybe we can also upload the paper if you have more interest in this. So now I think maybe Katerina, I can get back to you, and if you have any question, I'm happy to answer all of them.
Thank you so much for this amazing presentation and for explaining to us this really interesting technology. And
thank you so much.
Yeah, and I know that Armish, he had a couple of questions already in the chat before, so I wanted to give him an opportunity to ask right now. Hey, Armish, please.
Perfect.
Thank you, Katrina. I think some of my questions got answered by Richard, but here is my doubt or sort of curiosity. Uh,
Perfect.
what sort of governing equation describes or determine the flow at such a microtubule level? Do we see parallels? Do we know that the Hagen-Poiseuille equation describes the flow? If not, then are we relying just on the strong magnetic pull we would create, and it would just suck in the particles to the designated location? Uh, and then my okay, so my third last part of the question is that would we have an animal trial at some point of time out of simulation? How close are we for a trial like that?
Wow, this is an excellent question. So, you, Amish, you really like expert in the field. They are really like, you asked the perfect question. They're really really good, and so I can understand. You already understand a lot, so I can explain more details, I guess. So. I think the reason we choose this Hagen-Poiseuille law to describe the flow, because we are, let's say, in this case, as you can see, we are kind of looking at the vascular application. So if you think the vascular is the tubular shape, then yes, I would say they will be governed by the Hagen-Poiseuille flow. But you're right, blood is not a Newtonian liquid, which means they are, because they have blood cells into it. So they are not that easy, or you will be just a parabolic profile inside the blood vessel. They are definitely more complicated to that. I completely agree. And also certain cases, for example, people have this also I'm not really expert in this medical application, but some people say this aneurysm, they are driven by some local vertex in the flow. So, which means this verticity flow, not just just linear or laminar flow, can be even in smaller vessels, which is true. But in the heart, of course, they're just keep pumping. They are definitely nothing close to this Hagen-Poiseuille, but that's definitely not the area where we're looking for the potential application for that. But if you think of something really gets smaller and smaller, especially smaller than the 1 micrometer for the diameter of the vessel, then it will, I will say, more closer and closer to the Hagen-Poiseuille flow profile, to close to its parabolic profile. I guess that probably, hopefully, that answer your first question. And the second one, your comment is really. Sorry, could you remind me what is that? Sorry, I a little bit forgot.
Yeah, I was trying to understand, are we relying on the strong magnetic pull? If
Yes.
yeah.
Perfect. Sorry, I forgot. So in this case, we did not apply or use any magnetic field gradient. This is the very important point. So that's actually the key point for this. So we only apply a uniform magnetic field, which is much easier to apply. So I think because you already understand, if you, it's like the two magnets interact with each other. If you have a very strong magnet, you can also drive any magnetic object with the magnetic gradient field, right? And one of the limitation is this mechanism scale very bad, so similar. So you can imagine this is proportional to the local gradient, which means as a micro robot, let's say I know I will move to the position which has a stronger magnetic stronger magnetic field, right? If I'm free floating. So then that really requires the local gradient field. So if as a micro robot, which is let's say about a hundreds of micrometer in size or tens of micrometer in size, the field they feel is very small difference. So you need a very, very high local gradient. That's almost impossible in this case, especially if you think of application. Of course, if you're close to the gigantic permanent magnet, the surface have very strong gradient. But if you put in the brain, so like if you for brain or any potential medical application in the human body, you cannot, let's say, get too close because they're inside the body, right? So it's not cannot that close to a permanent magnet. So that's also limited potential to use the gradient field to drive this. So instead, in this case, on the artificial microtubule, you see this small magnets. So this nickel has a very strong gradient locally because they are really, really small. So from the size-wise, this anchoring effect, so you can use as a stepping stone to move forward, is pretty strong. So if, let's say, in our case, at least with water, it's just when apply a very fast speed, we never observe this. They always anchor on and move perfectly in a way. So we also definitely, of course, blood is thicker than water. We did not really, to be honest, we did not really perform any blood-related experiments, but we expect it will work in a similar way. Yeah. And the last question for any animal trial, that's a perfect question. That's we haven't achieved anything like that yet, so I think it will be possible, but the devices also need to optimize a little bit. Right now, I think we need a little bit coating on the surfaces for the mechanically more robust. So it's kind of working now, but sometimes if you pull this too much, they can break as well. So I think that there's something we need to improve on these devices. And another thing is we also need to think what kind of really the target application for this, because sometimes if you have a large tumor, you don't need this small device to deliver the drug into the tumor. You can just use standard catheter. But I'm also trying to work with other collaborators to seeking opportunities for potential some cases which come on to deliver drug into very small vessels. Then maybe we can consider more realistic animal studies for such applications.
Awesome, Richard. Best wishes. Just last point. I think it's more of a point. If you really know where this application is going to be, I think that would help you design the product better. Because let's say if it's going to
Totally.
get delivered under anesthesia, so
Mm-hmm.
the whole blood vessels, the shape of a normal human body is in a certain shape, right? Rather
Yeah.
than, and so yeah. So I am just thinking about how the external force is going to interact with this tubule at a different condition. But if you're really specific that okay, this is going to get delivered under anesthesia, so we know how regular human bodies. Yeah.
Ah.
So that's basically the area where we can do some simulation. Yeah.
Well, yeah, that's a fantastic suggestion. Thank you so much, Hamish.
Yeah, thank you so much for those questions and for answering those. Dr. Shah, Dennis, Joyce, Maya, did you have a question? Please flash your microphones and go ahead.
Yeah, thank you so much, Richard, for sharing such a wonderful work with us. So my question is about kind of a structure of the swimmers and the possibility of, formation of the microtubular aggregates. And in the same time, when we are thinking about the delivery of the nanoparticles, we know that the nanoparticles have a different, feature, and some of them even more has a potential of self-assembly and causing aggregation somehow. This is one point, and another part that I was just wondering about the immune cell, which you know that when we are talking about the blood vessel and plasma is a site for the maturation of the immune cells, and somehow it is very important we are using what zone for maturation, and that's why it's a matter of the delivery of the particles or whatever. I was just wondering to know your opinion around this idea.
I think that's also a fantastic question. So regarding the your aggregates, I think that's totally correct. So I think there are many magnetic nanoparticle or something very powerful. So because as I said, like usually for many, let's say what people imagine the application for this micro robots, then you need to carry both drug and magnetic material on it. So what we use, for example, the one you see in this composite microparticle, actually they have a very small amount of magnetic nanoparticle inside, even though they use iron oxide, which is pretty strong, but uh, they're not like the whole volume is. It's like I think probably just very few of them. The magnetic pretty weak. So the reason why they can also walk on it is because the artificial microtubule provide a very strong interaction with them. So the magnetic of the artificial microtubule is strong, even though we are not really optimizing it. We just use this electroplated nickel, which is definitely more room. Let's say you can use nickel cobalt to improve the magnetic property for this artificial microtubule. So there's room to improve for that as well. And as you said, this aggregates is totally. We also try with this. I think some other I think for the magnetic aggregates, they usually depends on their geometry and also their magnetic property. So, so I think I I don't know what kind of magnetic nanoparticle you are talking about or you have in mind. But definitely, if you use pure iron oxide nanoparticle, for example, they're really small. The aggregate looks quite different. So I think I did some experiments, and sometimes because they also at nanoscale, this surface property for those nanoparticles is very important. And I can't say for many cases, but I think I remember they kind of self-assemble into like a blob of like a rod shape, which I'm not even sure why, and they kind of can walk on it. And it's not like all, and they also have a different type of assembly. And the reason why we choose this specific microparticle is because also there's no, let's say, there are particle coupling between them, because that would make the prediction or the assembly much harder to predict and to have overall view of what is going on there. For example, we also try with the neodymium iron boron microparticle, which is similar size as we show it here. And because neodymium iron boron has a high coercivity, so they have a they kind of, each magnetic particle have their magnetization, have their own preferred or already pre-magnetized direction. So they just form their own direction. They don't really form this nice similar size blob of particle to move forward, rather than they can become a huge blob and sometimes they're just a few. So they're highly irregular. So I guess in the case we want to show the small local motion, we just show this because they are nicely, you can totally see they have effective area, and they are assembled roughly similar size of blobs, of course, depending on local density, but they are moving quite nicely. Yeah, so that's, sorry, could you repeat your second question?
Yeah, I mean, for that example, as you just mentioned, we can just
Yeah.
get the amphiphilic molecules, for example, and we can just think about the branch type of that. The second question was about the maturation of the
Oh, the immune
immune
cell.
cells.
Yeah.
Yeah.
I don't know much, sorry, about that, but you're right. I think at least for the macrophages, some other immune cell will definitely respond to this foreign particle. So I will not be surprised if you just say if you place there for a while, they will or they could encounter some kind of macrophage there, and the macrophage trying to eat it up with this with the magnetic particle on the artificial microtubule. Let's say while you are transporting it. But I think there's some interesting works from not from our group but from other groups. They actually try to modify this macrophages through the magnetic particle, because once they just take it in, right, they decorate the surface with something. When they take it in, then this macrophages is getting responsive to magnetic field, and they want to drive it to do something. Let's say to treat, I think, treat some like brain tumor, for example. And I think that's also maybe potentially interesting, because I'm pretty sure if you give the macrophages enough material, it will walk on this microtubule for sure, because this is like also, it's just anything close by magnetic, they will get attracted on it and just walk along it. Thank you so much. This is also a wonderful question.
Shall I ask a quick question?
Oh, please.
Go for it, Joyce.
Okay, well, I'm afraid I missed quite a bit of it, but so I'll just ask kind of a general question. What is your wildest hope as to what diseases it might be used in? Thanks, I'm done.
Wow, that's a that's a really difficult question, Joyce. I think I don't know. I think I'm still in the exploration stage. It's very hard to guess. So, as I think as you can see, I think they're mostly we do this work because of fundamental interest. But the artificial microtubule can provide a way either to somewhere which is very hard to access before, or some drug which have a very bad side effect. So I think, for example, I just imagine it, if you have let's say a micro stroke, like those brain blood vessels so tiny that the traditional method cannot go into it, then, for example, I think there's a well-known TPA as a drug to dissolve this local blood clots in the stroke cases, because they also have a very strong side effect. So of course, you just want to release in the where the stroke happens, and I think in that case, if you have a micro stroke in a small area, then maybe this can be as a application case they can deliver, or somewhere I think also see a case which they also use a very small microcatheter, because in the blood vessel to supply the eye is also very, very tiny, so they also make a very, very tiny specific microcatheter to deliver this drug into the eye, the artery which supply the blood to the eye, right? So if you release it there, the drug is not going anywhere else, but they just follow the bloodstream and just go to the eye area. They will not have side effect to many other places. So I would say I would not see a very widespread, let's say, they can be used for many. They are not really trying to solve anything existing method. They are more like a futuristic that we want to deliver something very small vessels, or release a drug which is a very strong side effect. You just want to go there, not anywhere else. So I think that could be the most potential to have a breakthrough, I guess. Sorry, I'm really not on the application side. Just give my
Okay,
best
that's
guess.
all right. That was a very good answer. Very interesting and very exciting developments. Thank you.
Thank you so much, Joyce.
Thank you, Richard, for this amazing presentation. I was very intrigued by this visual of the fluoroscope and the X-ray on the C-arm.
Wow.
That's a very cool visualization. I've never seen it like this. We have had some other presenters on nanobots and this sort of technology, and I was curious about the durability of either the microtubules or the nanobots that you've looked at, and the degradation of this type of technology, like the time scale of when it becomes no longer a viable machine.
So you're talking about like the whole life cycle for these nanobots, right?
Yeah.
Or maybe per
Okay.
per microtubule, right? Like, so you got the different microtubules. You're going to insert them at different times into the body, right? So, like,
Yeah.
how long does one microtubule last where it'll allow the the walking on through the like electric magnetic function?
Okay, so I would say the microtubule, yeah, I'll answer this both part. From the microtubule, they are highly repeatable. So it's not like, so the issue with it is this magnetic material may get gradually oxidized, but the speed is really, really slow in water or in the air. So at least for me, I've been using one microtubule because I kind of glue it on the chip so I can just, perform something easily. It's been a couple months and I don't see obvious very significant performance decay, something like that. So I would say for many stable magnetic material, or you can do a surface coating to prevent the potential oxidation, then it can last for pretty long. Of course, mechanical wise, they are also could be brittle. So we are also thinking maybe do a little bit coating like this optic fiber. So if you coat surface with something elastic, then they will, even though you have cracks, they will not propagate, and they will not break or anything. You can easily retract it back. So I would say the microtubule should expect similar as this standard medical catheter, or potentially can be something like that. And as you can see, after this delivery or imagine treatment, then we just retract it back, so we will not leave it there. So they don't have to be biodegradable. And in terms of nanobots, definitely if you think you deliver a swarm of them and leave it there, definitely the whole life cycle becomes super important because they will need to be biodegradable over time. And I think, there are many people use iron oxide, but I think the iron oxide is very small. I think like about 5 to 10 nanometer size. So they are not a lot. So and also if you can make it like iron, they are also potentially biodegradable, but the particle, not just the material, the format, this particle size also plays an important role here, because if you something smaller than a 5 nanometer, you can they can pass through the kidney and they can be accumulated in the urine, so you can easily get rid of the body. But if they get really large size, then I guess in the end they will be degraded by, I guess, macrophages, something they're gonna eat and then gradually to degrade it. But that is not a very ideal path. So I think people are still working on that. At least you cannot just put a lot of such microparticle into the human body and expect they will all be fine. I think there will be a maximum a load that will be the safe load allowed to put on it. So that's why we think, for example, this nickel rod that we show in the paper, it may be not very ideal for drug delivery because they are full of metal, right? But in certain cases, it depends. Sometimes the treatment want to be, you want to block, let's say, a cancer cell, like you block the vessel, the blood supply to a certain tumor, then, that will be fine. Like as long as the resurface cause something to protect it, and then it can stop the blood flow, and then the tumor will gradually shrink. That could be this kind of to trigger the thrombosis. I think there will be something potentially useful. But for the others, which, like say, I think they're maybe more promising that we show later with the small composite, mostly polymer particles, which they only have a few nanoparticles inside, but the most of the body, we can use, let's say, that biodegradable hydrogel as the main particle material, and we can just load drug into it. That will be, let's say, more promising, but of course then that will slightly weak, so that's why we need help with the microtubule.
Along the same line, Richard, thank you for the presentation.
Thank you.
Along the same line, so you're thinking, imagine that it is reusable and recyclable, and you can recover it just as easy as when you deliver it. So my question is regarding to the cargo. So the cargo size varies, right? So you can have a smaller cargo, a big cargo, depends on the purpose.
Exactly.
So if you want to deliver to a larger area, so what makes you retract. What would be a good localization, specification cargo you needed to carry on, localized, right? Because your drug, and then you needed to be delivered. What kind of things you're thinking with? Let me put it different. Hold on just a second. You know how, like, if you want to deliver to the brain, let's say you said you mentioned a stroke, so you want a specific region, basal region of the brain stem. So are there any ready target molecules or cues you already tested, coupled
we did
with your
not
microtubule?
really tested
Okay.
they're still not really drug tested yet. But I think you're right. I think one thing at least the field right now is considering is this TPA. I'm not really a drug person, but what I heard, what I have very limited knowledge on that, but what I heard that this is a drug, it's a very effective drug when people have stroke. So if you deliver or if you just inject it into the bloodstream, then they can dissolve many thrombosis in or the blood clots that block the vessel. So they can really very effective to treat the stroke. But the reason why the doctor don't use it much because they have a very strong side effect. They're bleeding elsewhere. So that's kind of like a double edged sword. So it's not like a safe drug to use. So many doctors really concerns a lot when they're using it. So some cases they think the risk is higher than the benefit. They just don't use it. So, but if you think of you can deliver locally, the things could change, right? Because you just give the area which had blood clots or the thrombosis, and then you can dissolve locally. Then you can have much higher confidence to use a slightly higher amount, right? Then that give you advantage for this targeted or very localized drug delivery. So I think that could be. At least from the starting point of it, make a lot of sense to do this. But I have a very limited knowledge on that.
All right. Can I jump in and ask a couple questions?
Oh, absolutely.
All right. Well, thank you for this presentation, Doctor. And this is fascinating stuff, right? So I just want to get a couple little quick clarification. Because I just jumped in the kind of like latter part, and I've been looking at the PDF here. So on, I guess, slide number, where's that at? Let me find it. I'm looking on my little phone here. Okay, because it seems like, okay, it goes through the tube, right? It goes through the tube, and then it's going to get to the little magnetic delivery function, right? So does it do the delivery? What I'm trying to understand, where is that slide? Give me a second. What I'm trying to understand, I guess, is Yeah, here we go. Okay, it's the second to last slide, I
Yes,
guess number 13.
exactly.
It says medical catheter to AMT to microbot,
Yeah.
right? Does that mean that? So I see the so the medical catheter is the medical catheter, and then is that micro the magnetic railway that it moves down,
Yes.
right? That the cargo moves down. Is that all the way back to the beginning where it's inserted, or is that like the cargo goes floating down a tube and then the track is towards the end and then they all line up on the track and go down, or is that magnetic track all the way back to the very beginning?
They
of the catheter.
Yeah, so the track should be connected to the catheter because the track is like a fiber. So the way we implement this, I think they should go through this micro catheter because we already know that this catheter or let's say the smallest catheter we can buy available on the market, they can already work really well, right? So there are a lot of doctors have experience with it. So the question is about how you can go deeper into the microvascular structure. Can you be more precise in certain need?
Exactly.
And that's how, let's say, you can just push through like a really small, very thin fiber, this artificial microtubule through this microcatheter, and then you start to rotate the magnetic field, and then any magnetic drop, let's say, close to the trail, will just walk on it, and then just robustly follow the lead of this track and into this target position. And then when you go to the target position, maybe let's say really, really tiny vessel, then the flow is almost negligible or really low speed, and then the drug can release it there and maybe can finish the maybe a last few minutes. And to be honest, I think maybe you can just randomly release it. That's also be fine. That's, I guess.
Yeah. So it looks like so I guess my question is that track running the full length of the catheter, or is it just at the end where like the cargo goes down and then they jump on the track and it's almost like a little tongue, or you just stick it out,
Yeah,
you get to
exactly.
you push the tube as far as you can go, and then you like it's almost like a little tongue or a little
I will
butterfly or something,
imagine
then
that way.
this sticks out.
I will imagine that way. So
Yeah.
but for the real application, this town, as you said, like this artificial microtubule, they will be connected to, I don't know, let's say we can make a wire on the back, let's say metallic wire or nitinol wire, which is, we know, very stable and stiff, and then they also flexible, can follow the trajectory, but we don't have to make all the way back, let's say 2 meter long artificial microtubule, right? That could be redundant. Yeah. That's how I feel.
Exactly. Yeah, you don't need to, you just need to get the cargo down to the end, and then you just need a little small space to
Exactly.
let the ride it on the track, right?
I have a
So then the next. Hold on. Let me. Amish, can I finish? Let me go over this. Hold on a second. Right. So then, okay. So then the next. So I understand that. Then the next question I have is around power consumption. Is that so? The battery, the magnetic. Movement down, you're doing that with I guess an external source. Absolutely. To charge it up and push it down, right?
Yeah.
And then what's the power needs? Is it low power or higher power? Like what's power needs for this?
This is a perfect good question. The power, it depends on what kind of magnetic system you use. For example, if you use the one I think I draw there for maybe the slide number 3, do you use a robotic arm to hold a magnet at the end, and then your power will be the robotic arm, whatever you consume to rotate the magnet. But in other cases, for example, we use electromagnetic system, which means you pump a lot of current into the coils to drive this, and that's much higher power. Let's say for in the medical or clinical setup, that could be a kilowatts or even higher. I think we use 40 kilowatts, something like that. It's pretty high, but the advantage for such system is you can just turn off the field, which is much, let's say, much safer than the robotic arm in a clinical environment, because those magnets, they're pretty strong, but not as dangerous as the MRI magnet. This thing will get attract to it, and I don't know how that will work out in a clinical setup. But they are different system, and then different have they all have their advantage and disadvantages. But they are not like insanely high power. So I think in a clinical setup, those kind of power should be acceptable level in a way.
Okay, so the next question I have is that length, what is that little track they're moving down, right? The little magnetic track.
Yeah.
What is the dimensions of just that track? Like, like in millimeters, let's say like 1/1000, or like what's or 1/100. I don't know. What's the what is
They're exactly roughly the size of the hair. So they are 50 micrometer in width and I think 80 micrometer in height. So they are roughly like the hair, but they can be, I think our sample may, let's say, 2 or 3 centimeter long. So the length is very long, but the width and height is very, very thin. So they are exactly like a hair.
So the width, okay, the width and height is exactly like a hair, including the cargo floating on, moving on top of it, or not including the cargo?
No, not including the cargo. But the cargo is roughly
Okay, got it.
dimension. Yeah.
Okay, this is fascinating stuff. Okay, let me tell you why. Right,
Wow.
this is really cool stuff you got. Right, it's not just for medical, bro. Okay, you could okay. This is. I've been looking around and trying to find stuff for a while. I'd like to talk to you about utilizing this technology in the augmented reality world.
Wow.
Right.
Mm-hmm.
Yeah, and not necessarily through the body, but externally, not inside the body, right? So because, all right, so here, I don't mind mentioning it. This needs to come out to the world, and hopefully, and it needs to be open source. This piece of information has to be open source, right? Because in the augmented reality world, needs to be. This piece is what unlocks the whole augmented reality world. Okay, right now in AR, right?
Mm-hmm.
Imagine you have AR glasses on, right? And by the way, there's a lot better stuff than Apple and other guys' stuff. Let me give you some links to look at, and then we can talk later. So if you look at Immacula.io, EMACULA.io, Immacula.io, you'll see they have what I believe to be the lead in AR holographic display technology, which is lens and filter. So they have a little 2-minute, 3-minute video. So that's Immacula, right?
Mm-hmm.
Right. So I know the CEO there is my friend, right? And then there's also 2 other platforms that can, potentially be we're talking about integrating, which is sensoryx.com. That's the CEO there, Dr. Rolf, is a friend of mine. That's who we want to get on a call with, on figuring out your tech and his stuff. So he's got glove technology for the augmented reality world, and it's got sensors on it. So yeah, sensoryx.com,
Mm-hmm.
and he's got the best gloves for the AR world, right?
Wow.
And the last one's going to be that you want to look at is, yeah, exactly, badass stuff, right? Virtuix, and I'm invested into Virtuix. Is another friend of mine that actually developed locomotion in the AR VR world. So that's the Virtuix Omni. And so if you went and looked in YouTube, Virtuix Omni, it's freaking mind-blowing cool stuff. Same thing with Sensory X, right?
Uh-huh.
Now, I mentioned this because here's the deal, right? If you got your glasses on and you have a hologram in front of you, let's say you're standing and then you have a hologram of a door right in front of you. The door has a doorknob on it. Okay, you go with your gloves, right, to go reach in and turn the door. Right, you're gonna grab the door handle. It's a knob, and you're gonna twist it, rotate it, right, to open it. Now, the problem in the AR world right now that exists is to create the resistance. If you go grab it right now, it's just like, it's okay. Are you around it? Your fingers can kind of go through it. It's not fluid, right? And it's not like you don't have any resistance. You don't feel like it's a doorknob because there's no resistance back to stop your hands from squeezing in, your fingers from squeezing in.
Yeah.
So AR needs to take the physics of the real world of basically creating locking the joints, okay, to mimic resistance in the real world into the AR world. All right.
Yeah.
And in order to do that, what I thought about was utilizing. I was like, okay, you gotta have a polymer. So imagine a glove, and then there's like a thin layer all around the external part of the glove. In there, you have running. Let's just use one finger at a time to be easier, right? So you got your index finger, and let's say the inside of the finger where the palm is, and you have a strip, right? A strip running from the top of the finger down to the bottom of the finger. You got 3 joints there, okay?
Mm-hmm.
If you had a strip there on the bottom side and top side, and you had a polymer in there that you can adjust the viscosity level from stiffness to soft or liquid, right, at different varying degrees, at let's say every 2 millimeter point even, or 3 millimeter point, or every millimeter point, like a little sack, you can adjust the viscosity level. A polymer that can be electronically charged, right?
Mm-hmm.
To do that, but you could do electromagnetics, right? So when I looked into this, the solution that we're all playing around with is ferromagnetic fluids, because then you can have the magnetic charge at the top and bottom, and then create the various viscosity levels, right? But then I'm looking at yours, and it's very similar stuff, right? If you're able to kind of control the magnetic field, and I imagine the cargo as you're moving it down, and that's a very interesting way you're doing it. So when I was looking at that, I was like, okay, that's efficient, because then you could still use that where and have just one. You basically created, instead of having two strips where you need a strip at the bottom and a strip at the top, and a magnetic, you activate positive, negative top and bottom to move stuff through.
Mm-hmm.
You just you're doing. I see how you're doing it. It's very clever. So it's more efficient, right? To where and it's less space too, right? So the cargo's moving along there, right? Now in the catheter though, right? Think of the catheter format, right?
Mm-hmm.
In that catheter, if you had you had that bottom layer tube, and then you had the ferromagnetic fluid, and it basically just charges up and creates stiffness, and you can direct that to specific points on the finger, through a bunch of, and I don't know exactly how it would be done, rather than having a bunch of little wires going all the way down every millimeter. It'd be nice if you can basically activate somehow on the track. Like, let's just activate, if the track has 100 points on there,
Mm-hmm.
right? Position 1, 2, 3, 4, 5. If you can, from some other point, activate just, let's activate sections, 25 to 30 to be stiff, right?
Yeah.
35 to 45 to be medium, right?
Mm-hmm.
And if you
Mm-hmm.
could do that, now we have basically cracked the biggest problem in AR right now, right? And doing it now, the issue with utilizing ferromagnetic fluids
Yeah.
is, and this approach is the power consumption that would be required to basically have that much, because you have the whole body, right? And or at least the gloves, right? The gloves on the front and
Yeah,
back
that's
side
pretty
to
high
basically
power, I
start.
guess.
Exactly, right. So bringing that, like, what would bringing that power down, right? But even then, gamers and I mean the medical professionals, doctors, the use for this is so vast that even if there's higher power consumption in the beginning, that's okay. People will still jump on this, right? And then maybe over time you can get more efficient or
I
something,
think you're
right?
mentioning a
Like, what would
very
be?
interesting question. I think yeah, if I understand correctly, you're talking about the variable stiffness control. Basically, some people use different material, and you're considering using ferrofluid as a variable stiffness control. There actually is a good idea, because that's how the car damper, magnetic damper, because the magnetic alignment can drastically change the viscosity. They can give you this kind of resistance as you want. I think it's quite, it's not a bad idea for this AR, let's say, gloves to give you this, the right touch or the sensation. I think it's right. But as you said, like, I think there are probably two issues with it. But one, as you already mentioned, the power is not going to be small, right? So you need a lot of coils probably, or other method to drive it. And the other is the magnetically, sometimes they can be local, but for our case, you can see they are kind of global magnetic field, because it's not like the other actuator magnetic. If you turn on the global field, everyone will suffer. It's kind of breathe in or emerge in this magnetic field. Everyone will be, and everyone will feel the same. It's not like I just turn on, you feel the field and the other place don't. So that's not. I think that's just not really magnetic system works. So they have to. Usually, in our case, you have always generating a large magnetic field in the workspace, and then everything will govern by the magnetic interaction inside the system. So I think what you're looking at should be something, not because if you have AR assumption, you will not usually want to need a large magnetic setup to drive this, which will be acceptable in the clinical setup. But for this kind of, I think, consumer electronics, it should be something, I don't know, like then you need, as you said, you need to think of I don't know how this be some local interactions between your ferrofluid and what kind of the magnetic interaction, the strongly magnetic component other than the ferrofluid inside the gloves, and then they will give you the strong interaction which can provide this touch or the drag as your. Is that something you're considering?
Yeah, yeah. So you were going down the right
Yeah.
track there, right? Hello, can you hear me?
Yes, totally.
Yeah. So it, like, with this application, I understand that you guys are using the external source because you're inside, right? But if you're already external, if you're already outside, right, you can you can charge, like, having an external third apparatus to charge the track, would not be ideal. It'd have to be somehow charged through the track itself, right? Like you can go in and track,
That
to a
will
certain
be
point. And
amazing. I think you are talking about something will be really cool, because if that can be realized, as you
yeah.
said, you don't need external setup. That would be great.
Mm-hmm. Mm-hmm. Exactly. So let's do this, okay? Right? If you want, like follow me, and then I sent you a message, I think, right? And then
Absolutely.
if you have WhatsApp, we could jump on a call. I'll get Rolf on the phone, the CEO of the Sensory X, because like we're already working on this stuff, and then we could jump on and just brainstorm and see if there's a opportunity here to basically utilize your tech approach, the approach you're doing, with little modifications for the AR gloves.
I think we were thinking, not the AR glove, but we were thinking solving something like you mentioned, can we, how, because right now the magnetic interaction, as you said, driven by the external setup, and they are, let's say, they will be pretty expensive. They will not be something really cheap. But can we use something, let's say, locally to switch the magnetization? I think they are at the nanometer scale, so you can use it like current to swap the magnetization nanomagnets
Yes,
by some
exactly.
spin orbit coupling that exists there. But they're not able to scale up because they are, I'm talking about in a few nanometer scale, like in 100 nanometer. But let's say this medical setup or many of the applications, let's say the gloves, interesting, they're much larger, and then that is something a little bit missing in the range. And I think the existing or the technology will be used coils, and the coils, I can imagine, they're large, they're heavy, they have disadvantages. So that's also people looking into, I think, how we can couple magnetic and electric material and the meso scale, something for various kind of application to provide feedback. I think maybe you should look into, I think there's a quite interesting paper by John Rogers. They use this vibration to provide the sense of touch with a different tuning frequency by John Rogers, using the very small permanent magnet and the coils. And then they can provide this, as you said, this is sensory feedback, but not the ferrofluid or the resistance, but the other type of sensory feedback, like the touch feedback, using a high vibrating signal to mimic or to simulate how we feel from the surface. If that's something you'll be interested, but absolutely, if I have following question, I'm very happy to discuss with you for any brainstorming. Yeah, if you are interested in this direction. Yeah.
So I think, let me see, let me double check. I think I sent you a message there.
Absolutely.
Here, I'll do it right now. So I'm gonna send you. So if you just kind of send me your number, and then we could jump on I'll do a little WhatsApp group with the CEO, and then we could jump on find a little time there, because this will be it'll just be a fun call to get on, dude. I'd love to.
Yeah, I think we also missed one of our mission question for previously. Yeah.
Okay.
No, that's okay. But Richard, my question was when Maya was asking, right? So how this track's gonna, what would be the initial starting point of this track? And you said that okay, there would be the point where the microcathedral ends.
Mm-hmm.
From there, you're gonna right. So I think there are a couple of design issue with that, because in that case, you're gonna be driving or guiding or controlling that magnetic track via cathedral, but not directly. But if you have that track going really up to the beginning of where you insert it, you would have the direct control of that track. So that would actually increase your problem. It's like controlling another pipe with a different pipe.
Mm-hmm.
So I just want to put this out. That's if the track somehow, you might have to create a different cathedral slot itself, which can accommodate this track and go up to the places where the cathedral can go, and then from there it extends, because it's all about guiding and navigating that thing. How are you going to do that? Because putting the fluid through the track is one problem, but guiding that is also another problem.
Mm-hmm.
Yeah, so that's just my 2 cents, and that's where I was trying to come in and say, okay, I think that's a problematic design.
I completely agree. I think you're really pointing this, like if you consider, as you said, like this process, the guidance with the catheter and the guidance with this track, they're both is a problem. And but they are kind of like the other aspect in this application that people are looking for, how to this guide wire. There are some already established guide wire, even magnetically guided catheter. So the catheter, they also sometimes they have this pull wire. You can just pull and the tip just tilt, and then you can use multiple tools for this interventional surgery. So I think, of course, with their magnetic ones, maybe it was slightly easier for doctor to operate it. But even though there's I think state of the art, they're using this guide wire, repeatedly swapping the guide wire and the catheter to go to the right position, the right location, and that's kind of that's how I think the standard practice for interventional surgery. And I think you also mentioned another important aspect is how this interaction between this fiber, and this catheter, right? And I think there also could be some opportunities there. I would say if they really find some interesting application for a specific location we just want to go, and we can even customize the catheter for that, and the microtubule can even be part of the catheter, like they can be merged into one object if that is a good idea. But I don't really know, so this really depends on the application case, I would say.
Yep.
But thank you so much for these comments.
Yeah, thank you so much for this amazing discussion, and that we got maybe a collaboration going on for the future.
Sounds really, really, really stimulating, actually.
Yeah.
Maybe I'll ask him. I'll ask Dr. Rolf and see how willing he is to come on Clubhouse to talk about Sensory X and your tech. Like if we had a joint session, right, with you and Dr. Rolf, right? That would be pretty interesting, right? Like, and he's, he's already commercialized and in there, and like got all types of IP and whatever. But this piece here, I think it'd be kind of nice to jump in and like brainstorm about it in a room, or at least, or we could start on the call to see what set that call up. But this is, I just want to like, I'm telling you, man, I'm super excited because this guy is a genius, man. Like what he's done over there and the speed at which he moves, and he just didn't do the gloves. He did this external sensors. He's creating so much stuff in the AR world at blazing. Like this dude will come up with a prototype with hardware in like a week, in a few days. It's incredible what his capabilities are over there. I know he's in Europe. I think he's in Switzerland. But
that's because Richard, he's in Constance, Germany, so it's right next door.
Yeah, right next door.
Yeah. Yeah.
Yeah,
So
let me know if you need help setting things up, or
absolutely,
for Clubhouse. But
sure. I'll ask him. If he'll come on here. I don't know that he's a little shy, right? But I'll see if he can. I think he will. I think he'll come on, right? I can convince him to come on, right? So that would be yeah. We can talk about it, set it up. It'll be kind of fun,
Sure.
So
that's
yeah.
I'm always happy when there are collaborations starting and projects starting.
Yeah, and also welcome. Yeah, definitely.
No. I mean, this thing is like the biggest thing in AR. Like the cracking this problem, right? This is what's needed to unlock the AR world right now.
Yeah, I agree.
To
it's
like really
very challenging for this haptic feedback.
Yeah. Yeah. And it's not, and see, everybody calls it haptic feedback, but it's not haptic feedback. It's resistance, right? It's a different thing. Because like, okay, for example, right, there's this, actually there's another company called Haptics, Haptix, right? Haptics, they created this glove. They got like 20 million in funding and all this cool shit and whatever. But you know what? When you go put it on, it has 16 tubes coming into the glove. It has an air compressor outside. Okay.
I see.
Yeah, so it's like I put it on. It's like, feel this. It feels like a little. You're looking at a spider, and it feels like it's walking on your hand. I was like, okay, that's cool, right? But it's not. It's like this is not gonna work, dude. Nobody's gonna walk. Like people want to walk around externally in the world, in the AR world, just walk around and have their gloves on and have their AR glasses on, right? And a little headpiece and interact. They don't want to have some lugging behind them a air compressor for their gloves, and the same thing with the glasses, and whether it's Microsoft or all the other guys right now, you got to put a big old box on your head, right? That's just not going to work. That's not going to be the winning product. So Immacula has the winning glass tech, and they already did like a $4 million deal with DARPA. Now they're already they're going through FDA approval right now, um, for the contact lens tech, because it's also for medical use. And these things have crazy, like Steve Wiley is the CEO there. I talked to him. One of the things that when I had a session with him that he disclosed to me was they have 30. They have 30x zoom. I mean, imagine being able to walk around, dude, and like look at something and have 30x zoom. That's crazy. That's insane. That's what exists right now, right?
Wow.
And so, yeah, and
Yeah, I think also for prosthetics, it would be really cool because really good prosthetics should have a really good sensory feedback, which can actually even help patients regain mobility and sensory input over their actual body, like Miguel Nicolelis and showed this. So the better that would also work for like prosthetics, that would be also amazing, also for recovery. So yeah, I
Yeah,
think
you're right. I
yeah,
think this force or the resistant generation, or there's a force generation for the haptic feedback. If something can be done very well, that's really like they're really like a game changing. Exactly, not just for like AR. There can be many applications out there actually.
yeah, for example, in the medical use, like you could even like work out your muscles or something. If you have a full suit on all over the place and it's got these little areas that you could add resistance, so you could basically stiffen an area and release it, stiffen it, kind of creating a pulsing movement, right?
Yeah.
If you need to, like, you know, technically speaking, we could probably replace the straight jacket with this thing, right? Somebody acts up, good, they get locked up. You're in a fight, hit the button, you can't move anymore. Just solve the
Yeah,
problems
that's
in,
really
in
like a
prison. You know what I'm saying?
science fiction come true. Yeah, totally.
Yeah. Yeah, and this is kind of what I do, man. My thing is, I float at the 30,000 foot level and come down to like the 10,000 foot level, and the technology. I kind of translate between the technologists and everybody else, right?
Yeah, but I
So I
think you
kind of
get
like,
at least one thing. I think this is your direction is totally right. I think the magnetic could have some advantage at the small scale, like especially you can control with electronic wire somehow. That's this there's certain advantage. Let's say it's like when we play two magnets, their interaction very strong. So for this small, or let's say you won't have a size limitation, like if you put on the glove or some other thing wearable, you cannot, let's say, as you said, like pumps in, because then you cannot drag around this pneumatic pump behind you for those applications. If it's something portable and provide strong this force or this kind of interaction with especially the human body, then actually magnetic system is one direction to look at. There are definitely potentials in there.
yes, yeah, for
Yep.
sure, exactly. So I also sent you my LinkedIn in the message. You could send me like a request over there and check me out
Cool.
there, and then I'll send you Rolf's. I could probably just do a group chat on LinkedIn between me and Rolf to get that going. Um, and then yeah, it'll be kind of fun to go from there, because I really want to enter the AR world as fast as possible. So like my selfish incentive is not even money. It's like, can we just get this done so I can put these on, and like we now have the AR world. Like this is what's needed, and if we make it happen, we just opened up the AR world. That's what's waiting. This is the last piece that's needed.
Wow, that would be amazing.
yeah, great. Thank you so much, Mayor. This was such an amazing room. I don't know if you guys want to keep chatting, or because it's almost 2 hours are up. I didn't want to take, more time of Richard. I don't know what time it is, but it's getting late for you too. So um, I'm looking forward for, to hear, keep me updated how things work out. I'm happy
Absolutely.
about the outcome. And yeah, feel always free or welcome to come back, Richard, with updates, maybe on other projects that you're working on. And yeah, we are so thankful that you came here to share.
No, thank you so much.
To
It's been great pleasure with all this really expert question. I think I'm also very inspiring talk. So it's a great pleasure, and thank you for the invitation. Thank you so much.
thank everyone for coming and asking great questions. Maybe even having new projects after this. So it was amazing room. I really appreciate everyone here, and yeah, I hope I hear you all back soon. We'll have tomorrow quantum physics room related to quantum consciousness. There are some new results from like real world experiments, and it's kind of not looking that good for the quantum consciousness theories out there. But if you want to learn more and discuss it, come back tomorrow at 2 p.m. EST. So thank you so much, and enjoy the rest of your day, evening, morning, wherever you are. Thank you.
Thank you so
You're
much.
welcome. Bye bye, everybody. Thank you, guys.
Thank you. Bye. See you next time.